Hi, we're Design Team 6. We're sponsored by the Resource Center for Persons with Disability. Our project is a Bluetooth low-energy beacon. I'm Nick Blackledge.
I'm Boy.
I'm Stephen Lee.
I'm Chunyang Chu.
And I'm Mass Marion.
Okay, I'm going to give you a brief introduction. Michigan State campus consists of 538 buildings spread over 8.125 square miles. Navigating through campus is a daunting task even for people with normal vision. The challenge is significantly greater for the visually impaired, especially rushing through unfamiliar locations. 20-minute class interval change are insufficient for the visually impaired, and the risk of injury are increased while rushing through campus. Our team, along with the RCPD, have developed an interactive indoor location system as a solution. The solution is to use Bluetooth low-energy beacons placed around campus that will communicate with other BLE-equipped devices such as smartphones or tablets. The beacons can be placed on building entrances, exits, hallways, and inside classrooms to provide a highly precise and accurate location system. The beacon sends out a signal at a specified time interval that will approximate the beacon's distance. Once a phone comes in range with the beacon, an alert can be triggered on the phone and will let the user know the location and distance. The BLE beacon provides a low-cost and low-power solution.
So I'm going to talk about some background information about the Bluetooth 4.0 we used. It's also called Bluetooth Low Energy. It uses the 2.4 gigahertz frequency range, and as you know, the Wi-Fi is using the same frequency band. So the Bluetooth 4.0 implement 3 advertising channels located at the beginning, the middle, and at the end of the frequency band to prevent interference. And we can also adjust the broadcast interval from 20 milliseconds to 10 seconds, depend on your target requirement and how much power you need to save by increase that interval. And about the beacon packet, we modified and added some information into our firmware to suit the iBeacon standard from Apple. The UID, the universally unique identifier, is the kind of identity information for our beacon, and we use the following string for this value, and it's usually the same for beacons produced by the same manufacturer, and that's why the major and minor numbers are introduced to distinguish between each different beacons. And here's some design specifications for our beacons. Of course, we use the Bluetooth Low Energy technology to be compatible with the Apple's iBeacon standard, and the price range for our beacon should be less than $20. So if we want to mass produce it and implement it throughout the college, the overall cost wouldn't be very high. And our beacon should be also temporal resistant, so the identification information within each beacon will not be altered.
So probably the best way to understand what beacons are and what they can be used for is to demo them. So we have a quick demo here. Command F for full screen. Okay, so what you're seeing right now is a live screen of what I have on my phone. And what this screen is showing is basically what the application can see of our beacons. You can see we have 3 beacons broadcasting in the room right now. These numbers are the major and minor. That's what we use to identify individual beacons. And then, based on the signal strength from the beacons, we're able to calculate a distance, a rough distance. So it's live, or it's real time. So as I move my phone around, it should update in 1 second. So this is beacon 1-1. You can see we're about 0.2, 0.1 meters away. Then if I walk around over here towards beacon 1, 2, and 3, 1 over here, those distances will start to decrease here. It's a little slow. There's some averaging because the spectrum is very crowded. It's 2.4 gigahertz. It's the same spectrum that's used for Wi-Fi. So it uses averaging, so it takes a little bit of time sometimes. So that's basically what the data the applications are able to see from our beacons. And from that, we can get a rough estimate of location. And using that location, we can trigger events. For example, one thing we can do is we can actually trigger web pages to load. I'm on 3G. This is loading our team website. Unfortunately, I'm on 3G and it's really slow, but that is one example of an event we can trigger. We can also pop up notification messages and maybe play media. Basically anything an application can do, we can trigger based on location. Now, because we're working with the RCPD, one thing that we also want to demo is the accessibility. iOS has a text-to-speech capability called Voiceover that is built into the operating system. So we have a little bit of a demo app here that...
We are in our demo region. Please place this iPod Touch at one of our demo stations.
It's just reading what we have on the screen. And so as I get close to this beacon, it will...
Alert. Thanks. You are directly above a beacon. You are directly above a... Okay.
And that's just kind of one little example application of how this might be used by a blind person. We're working with the RCPD. They want to use this for information displays, digital information displays. If you go down in the first floor of the engineering building, you'll see digital signage that you can actually touch and get information about room numbers and how to find them. And so what the RCPD wants to do is build these beacons in, and then they'll have an app, so that way a blind person will be able to have our app running, and when they're near one of these information displays, it'll give them some sort of alert to let them know they're near. They'll be able to go into the app and find all the information that's on the display will be able to be read to them by the iOS device. And so now we're going to talk a little bit about the actual hardware we built.
Our design is based on the ECE480 Bluetooth Low Energy chip. The chip was chosen because it provided the necessary functions while being low cost and well documented. Custom PCB was created to implement the additional circuitry required for the chip. The final board size is 1 inch by 2 inch, which would allow it to be mounted nearly anywhere. The final cost for an individual beacon is around $16. However, if we were to produce 500, the cost would be lowered to $10 per beacon. We developed a separate programming header as shown in the bottom picture, not only to lower the cost, but to also prevent tampering. In order to reprogram the firmware on the board, you would need to use the program header, which has pins that are used to mate with programming vias on the board. Therefore, it's more complex for just a stranger to reprogram it. As shown in the box outline in green, a PCB antenna, trace antenna was implemented directly onto the board. We chose this option because it lowered the cost as opposed to antenna component. As shown in the box outline in red, via stitching is used to enclose the RF path. This is done to prevent other noise from on the PCB from other noise from affecting the RF path. Instead of using a 4-layer PCB, like in typical RF application, we chose to use a 2-layer. This is also done to lower the cost. And all the trace is done on the top layer, while the bottom layer is used exclusively for the ground.
So for software, we have 2 applications built to interact with our iBeacons. We have Apple's iOS operating system application here, and an Android application on the right, that's from Google. The iOS has all of the iBeacon protocols already built into it, since Apple kind of headed the iBeacon idea. And then on the Android side, we had to use a library from Radius Networks, which provided a lot of the documentation, the objects, and things like that that we needed to be able to read constantly. And between the two, we have very compatible and similarly performing devices.
So 4 different stages of testing procedure were performed in our design process in order to ensure that our final design beacon obeys the iBeacon protocol and also has a performance comparable to the actual iBeacon devices. The first testing we did is called the packet capture testing, and we used USB Bluetooth adapter along with the packet sniffing application from TI to capture and display the raw packets broadcast by our beacon. One of such packets is shown here on the screen. These 2 lines actually represent one single packet. Because we need to ensure that our beacon is actually broadcasting the same way as an iBeacon device will. So the thing we need to check is this one here, this 6 bytes. This is called iBeacon prefix. So we need to see if these values match the iBeacon standard, and which it did. So that confirms that our beacon design is actually broadcasting iBeacon packets. Another thing we did in this stage of testing is that we also altered the major and minor bits over here to all the possible values from 00 to FF, just to ensure that we can broadcast any range for the major and minor bits as we need, just as the example over here. The next test we did is the connectivity test. In this test, instead of using a USB adapter, we used several mobile devices, including an iPhone 4S and several Android devices, to detect and display the packets we broadcast by our beacons. In this stage, it's also successful that our our mobile devices can successfully detect and display all the packets. And this also confirms the conclusion we had in the first stage of test that our beacon device is actually broadcasting iBeacon standard packets. The third test we did is called the maximum range test. In this test, we want to make sure that in a sense of maximum detection range, our beacon works just as well as the actual iBeacon devices. In this test, we placed an iPhone 4S acting as an actual iBeacon device, along with 2 Google Android devices, along with 2 of our prototype beacons right next to it. And we used 2 Android phones to detect those packages, and we move away with the phones to see when we lose contact with them. And the results proved to be successful, that we lose contact of our beacon within 2 meters of losing contact to the actual iBeacon device. And for all of the 3 beacons, the maximum range is approximately 50 meters. So that means like our beacon performed just as well as the actual iBeacon device in the sense of the maximum range. And the last test we did is called a distance accuracy test. In this test, we want to make sure that our beacon is displaying the distance in an accurate way. So we put the devices in 3 distance, that's 1 meter, 2 meters, and 5 meters, and see what the actual display is. In this chart, you can see that we used an iPhone 4S, a Google Nexus 5, and a Google Nexus 7 tablet in this stage. And at distance, this is the actual distance in meters. So at 1 meter, all 3 of the phones are displaying roughly 1 meter, and 2 meters also, and 5 meters. I think these 2 are displaying 6 meters, and this one is 7 meters. That's a little bit off, but when you compare to the distance performance in the actual iBeacon device, our design is still better. Because like when it's at 5 meters, the Android devices will display like 15 or 20 meters. That's pretty jumpy result, probably because the Android, like the software we use from Radius Networks didn't use averaging of the results, so it's pretty jumpy. For that reason, when we develop our own Android application, we enabled averaging, so it produced a more stable and consistent result. After all 4 stages of testing were completed, we conclude that our beacon performed just as well as actual iBeacon devices.
So looking toward the future in our design improvements, we have some PCB optimization that we can do. We could make the beacons battery powered because we're using Bluetooth Low Energy. It uses very little power. We're talking about years on a simple, small battery. And so if the RCPD wanted to pursue that direction, they could. However, we felt that being powered by AC would be easier, so that way you don't have to replace all the batteries, at least at this stage. Then we also have, on the software side, we could implement a database. So you have a database matching UUIDs, major and minor bits, to actual location names, so that you don't have to re-release all your software at once. You can simply maybe hit a menu button and say refresh the locations, the known locations. At which point the application could then, instead of saying you're approaching UUID blah 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 minor major this, it'll say you're approaching engineering building main entrance. It's just a much easier way to hear things. The other thing is improve the Android distance measurement. This is partially due to the Radius Networks library being less effective than the Apple, but it also has to do with the fact that you have many different companies producing many different types of phones, and so for that reason you get a mix of hardware issues with that. So,
Any questions?
To what extent does being on and using the 2.4 Wi-Fi network confound your results?
So the 2.4 gigahertz spectrum is it's called the ISM band, and it's an unlicensed piece of spectrum, for the most part. A lot of devices such as Wi-Fi, other Bluetooth devices obviously, but also even microwaves emit 2.4 gigahertz radiation. So we found that to some degree that our beacons performed differently. The accuracy depended on what environment we were in. For example, in the engineering building here, there's a lot of Wi-Fi hot spots, and that actually reduced our accuracy a bit. In other places, we had a better accuracy. The measurements we took here were measured in here, so this is kind of our worst in case environment.
I think what I'm also wondering is if I have a choice to use a 5 gigahertz network on my iPhone versus the 2.4, do you see a difference in the results from your implementation? Does it work better if I'm not on the 2.4 band?
Are you asking if you're also using Wi-Fi?
Data, yeah, if you're using data. I noticed you were on 3G, so I didn't know if that was part of a strategy to not confound your results or not.
No, we are actually my phone is hooked to using Wi-Fi to the computer right now. We did not test using different Wi-Fi spectrums.
I can't imagine it would be too significant.
Okay,
But
thanks.
Any other questions?
I'm good. Go ahead. You mentioned $6, $5 or something, $10.
$10.
Please. I'm assuming that in larger production that will even drop more.
So
Is there
the
a-
$10 component cost is at 500 beacons being produced. It does drop more as we go up from there. It's to give you an estimate for one beacon, it's the components cost about $16. So if you're just building one and ordering single quantities of everything.
So to equip the campus buildings, all of the buildings on campus with, how many beacons would we need per building, do you think?
it really depends on how much you want, how many points of interest you really have. Are you talking about just kind of like a center console where you have a directory and like you want to lead people there, or if you want to like mark all the entrances to the buildings? Because then, I mean, if you're EB has, I don't know, 6 entrances probably alone, and so I mean we have 500 buildings, so it could get up there very quickly.
The range is 50 meters?
Yes, maximum range is 50 meters.
So,
But that doesn't mean that you can't have multiple beacons within 50 meters.
Yeah.
Copy that?
Thank you.
Thank you.